All right, so this is our second lecture in the final lecture in Chapter 3 dealing with one-dimensional steady state conduction. We've covered a lot of ground with the plane wall and then radial systems, especially cylindrical, spherical, one-dimensional going radially out. Then we added thermal energy generation. That's a Q dot, a heat source, in the radial system or in the wall, plane wall and radial systems. Today we talk about extended surfaces. First time you see this, you say, what is that? Well, it's fins, fins, fins. That's what it is. So we want to talk about getting the fin equation for heat transfer. The easiest is to analyze a pin fin. So here is a surface, and that surface all has the same temperature, T naught. You want to promote heat transfer from that surface at T naught, or TB for base. And what you're going to do is you're going to attach a circular fin to it like that. So that's a pin fin. We introduce a coordinate system, X, going out. The length of the fin goes from 0 to L, and the diameter of that pin fin is diameter D. If you have convection, the surface of that fin is going to be cooled by the fluid. Often I think of the fluid as being cold compared to the base hot surface, so it's at T infinity, but that doesn't have to be. I mean, the equations work either way. And then here's the H convection coefficient. All right, want to find the governing differential equation in order to solve it with the boundary conditions to solve for the temperature at any location X as you go out. We're solving for a one-dimensional heat transfer. Our boundary condition number 1 is that the temperature at 0 is equal to the temperature of the base, or T naught, either one. Let me call this base temperature, TB instead of T naught. And then out at the tip you have some boundary condition. The one that probably makes most sense to you is, well, it's going to be convectively cooled at the tip as well. Mathematically, that works. You just get a more complex solution. Mathematically, the easier approach is to say that it's insulated at the other boundary. So if it's insulated at the tip, then the change in the temperature with respect to X at L is 0. So that's our second boundary condition. Okay, so how do we get our differential equation? That's the first thing. Then we get our boundary conditions, then we can solve for it. And then actually what we can do is later solve for Q, what is actually flowing, the total rate of heat transfer into the fin, and then that goes convectively off the surface into the fluid. Okay, how do I get my differential equation? Well, focus in on a small control volume, so you just sort of cut this disk out, if that makes sense. And you have the flow coming into that disk by conduction from the left, and the flow going out by conduction to the right, and then you have the flow of heat by convection off of the perimeter, off of that surface area of that little disk into the fluid. So when you get your differential equation, all it is what are the ins and what are the outs? You have a little puck type of control volume. And so the only in would be this conduction. Let me say that's a Q conduction at X. We're going to start X, and then guess what this location is? X plus delta X. Okay, and then we have two outs. We have conduction at X plus delta X. And we have the convection off of that surface area of that little disk puck type of control volume. Okay, so I'll rearrange this. I'll put negative q at x plus delta x plus q at x is equal to q convection. All right, probably the convection's the easiest to worry about. So it's just an HA delta T. So it's a convection coefficient. The area, now for the convection, if I tried to blow this up a little bit, it's this area right here that goes all the way around. So one way to think about that is talk about the perimeter P. For a round disk, what's the perimeter? Isn't it pi times d? Yeah, it's pi times d. So the perimeter times delta x gives me the convective area. Good. Okay, and then we multiply by the temperature at that location minus the fluid temperature. So that's our rate of heat transfer by convection off of that disk into the fluid. Okay, how about Q at x? Well, we're going to do conduction. This is at the location x. Coming in, that's Fourier's law, minus K A dt dx. What do you mean by A? It's going to be this area. Right away, the student can get confused by what area. The area for convection is different than the area for conduction down the length of the fin. And so this area, a lot of times I'll put a subscript C on it. Put a subscript C on there. Why do I put a subscript C on it? Well, it's a cross-sectional area that it's conducting down. Okay, in terms of pi and d and that, what is the ace of C? Isn't that pi d squared over 4? Yeah, that's it. So right away you've got perimeter pi d. Perimeter times delta x gives me my convective area. And then for conduction, it's pi d squared over 4. Okay, now you brought over this other term, you put the minus in front of it. Well, that's going to be minus k a sub c dt dx. Now, let's go ahead and be a little cautious. This one's evaluated at x plus delta x. This one's evaluated at x. All right. The two negatives become a positive. That helps us a little bit. And we take the whole equation, every term in it, we divide by KAC, 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 and then we also divide every term by delta x. But here I'm going to put it like this, delta x. We cancel the KACs right there. And then we focus on this term. I'm going to scoot down just a little bit. And so what do we have is we have the derivative, the rate of change of temperature with respect to x at x plus delta x minus the rate of change of temperature with respect to x at x. We divide that by delta x. That's equal to h p divided by k a sub c t minus t infinity. We are almost there for our differential equation. What do? You take the limit of that term as delta x goes to 0. New slide, jump over here. If I have, I don't know, 5 divided by x, and I say the limit as x goes to 1, what is that answer? It's 5, isn't it? Okay. Let's do the limit as 5 divided by x minus 1, and I say let's do the limit as x goes to 1. What are you going to get? It's infinity. And then we go, okay, you're getting good at limits, and that Okay, let's do this one. Let's do it at a y at x plus a minus y at x divided by a. And we take the limit as a goes to 0. Or maybe another way of writing that is x plus a minus x. What is that? dy dx. Where did that come from? From your 9 or 12 hours of calculus, plus your 6 hours of engineering analysis 1 and 2. So when we come back here and we have this, let's say the temperature at x plus delta x minus the temperature at x, and we divide by delta x, we want to take the limit as delta x goes to 0. What do you get for that one? Derivative of temperature with respect to x. All right, you're getting really good at this. One more. The derivative of temperature with respect to x evaluated at x plus delta x minus the derivative of temperature with respect to x evaluated at x divided by delta x. And we want to take the limit as delta x goes to 0 of that. What do you get? The derivative with respect to x of the derivative of temperature with respect to x. Another way of writing that, second derivative. Little math review. So now we go back and we say, hey, our fin equation, I know I kind of went off the page there a little bit, but it's going to be the second derivative of temperature. We're going to have this term, maybe I should scoot down so you can see it, HP divided by Ka sub c, T minus T infinity. Does that look like a good differential equation? Sure does. The book cleans it up a little bit and will introduce m as a parameter, which is the square root of HP divided by Ka sub c. Maybe in your math class you saw that and you say, why are they introducing this parameter? So fun, you know, it's kind of a funny parameter. And then the equation becomes the second derivative of temperature with respect to x squared equal to m squared times T minus T infinity. Why did they introduce m squared? Well, probably because they want to take the square root of that later. And the square root of m squared is simply m. Pretty slick. So there you go. Okay, but that's a definition of what m is. Hey, remind me, what is h in this equation for m? Convection coefficient. What is p? Perimeter, not pressure, perimeter, right? What is K? Thermal conductivity of the material the fin is made out of. What is A subscript C? Yeah, the cross-sectional area for the conduction. Okay. Then guess what? They're not done. They'll introduce theta. What's theta? The actual temperature minus the fluid temperature. Well, why? Because when they take the derivative of theta with respect to x, you get the derivative of temperature with respect to x minus the derivative of T infinity with respect to x. One of those terms is 0. Is it either A, B, or C? That's your first clicker question for today. One of those three terms is 0. Either d theta dx is, dt dx is, or dt infinity dx is. We'll stop. Okay, remind me, what is the goal of all this work again? The goal is that we have a coordinate system x, and our fin goes out from 0 at the base to the tip L. And we're really interested in getting a temperature. Maybe I plot temperature on the y-axis, and maybe the base starts at, I don't know, let's think about 90 degrees C. And way out at the tip, maybe it's down to, I don't know, 60 degrees C. So out at the tip, it's 60. At the base, it's 90. And it's going to have a profile. It could be nearly straight, nearly linear, but it probably not. It's going to have a little belly to it, okay? And so wouldn't that be where I'm trying to find t as a function of x, right? Well, why is it going down? Because there's fluid cooling it. There's T infinity, and there's H convectively around the surface of that fin. So when I come back here and I ask the question, is it A, B, or C that's equal to 0? Does the fluid temperature change as I'm marching further out away from the base? That's the term that's 0. So C is 0. This dt is non-zero, and my new variable, instead of temperature, it's a temperature difference. We call that theta, or the book uses the term theta. That's going to be, if I go back to this example, if I plotted theta, right, maybe the convection is, I don't know, let's make the math easy. It's 50 degrees C. Well, what is theta at x equal to 0? What's theta at x equal to 0? If T infinity is 50 and the base temperature is 90 degrees, theta is 40. All right, what's theta at L? 10. And so then theta would go from 40 down to 10 in this example. So that's what theta is. Theta is a temperature difference, T, which is a function of x, minus T infinity, which is not a function of x, a constant. Okay. So now we jump over here, and we have, we can cancel this out. And then you can take the second derivative, do it again. And so I'm going to go to another page, but we get a differential equation, which is the second derivative of temperature difference with respect to x squared is equal to m squared theta. We're getting it so abstract, Professor, I've lost all sense of math, and of heat transfer, right? Well, this is a slick way of doing it mathematically. Okay, then we have our boundary conditions. So that's our differential equation. Our boundary condition is that the temperature difference at 0, the base, is going to be the base temperature minus the fluid temperature, whatever it is. Okay. The other boundary condition, you could have what's happening at the tip. That's your other boundary condition. Now, we're going to set this up such that the derivative of theta at the tip is 0. What are you doing mathematically? Well, it's insulated. There's no heat flux going out the tip. All right. I know that we could have a different boundary condition, and you would then need to solve the equation. But the analytic solution to this one is the simplest. The insulated tip has the simplest analytic solution. Hence, that's the one that's used often in textbooks. Okay. So, you passed all those math classes. How are you going to do it? This one, we already did the easy stuff of separate and integrate. This will not yield to separate and integrate. So, for the first section of this chapter, we were just smiling and happy. It was just separate, integrate, boom, I've got the solution. The best way I can describe it is you pick a form of the solution. So in the back, somebody says, look it, I know that if I take e to the ml, let's say I try that, and I need to differentiate it. So let's say theta is equal to a constant e to the ml. And I say, well, what's the derivative of theta with respect to x if that's my pick, if that's my guess? What is it? Well, it's c m e to the ml. I shouldn't put L there. I should put X, right? That's what I meant to put, x. Right? And then I take the second derivative. Second derivative, okay, what do I get? Cm squared. Hey, you know what? That's probably why they put that m squared. You know, that's a little convenient. If what happens if I put a c1 and then I put a c2 e to the minus mx? Well, if I differentiate that, it'll be minus c2 m e to the minus mx. And if I differentiate that again, that becomes a plus c2 m squared e to the minus mx. C1's time, let's put C1 there. It would be like m squared times theta, wouldn't it? Isn't this is theta? Isn't this times this plus this times s theta? So the m squared comes out. And so you look up there and you say, that's it. I'm going to pick that solution. That'll take you so far, but then somebody else says, you know what? Let's try C1 sine of mx and C2 cosine of mx. That one will not work, because when I differentiate the sine, it becomes cosine. But when I differentiate the cosine, it becomes a negative. So actually, that will work if I had a negative m squared theta. But when I have a positive m squared theta, then guess what? That doesn't work. But something really close to it works. Not sin, but SINH. They're not COS, but COSH. Professor, what's that H doing? Get rid of it. Get that H out of there. No, what is the H doing? It's making a hyperbolic sine and a hyperbolic cosine. Sinh and cosh. Oh, haven't seen them in a long time. And last time I saw them, I wanted to say goodbye for the rest of my life. Seriously, I didn't want to see these characters ever again. Well, unfortunately, there's a few things that pop up in heat transfer that challenge you in your math. And this is one of those challenging things, because if you do the derivative of the sinh, you get cosh. Derivative of the cosh, you only get sinh without a negative. And so this works. You don't get that negative sign flopping around. So this one works, as well as this one works right here. Okay, wow, we have two of them that work. Which one do you want to use? And the short answer is if you have solved it before and you look at that tip boundary condition, that'll guide you. So if somebody said that the boundary condition isn't this, no, but it's that L goes off to infinity, and so then the temperature of the fin at x goes to infinity is equal to T infinity. Isn't it eventually going to get to the fluid temperature? It's infinitely long? Sure. Then I'll let you guess. Do you think A or B is the better version to use if you have an infinitely long fin? Would you want to use cinches and coches, or would you want to use the e to the mx and e to the minus mx? We'll stop it, and we'll just show it really is, that's the better approach. If you have a finite, so this is great if you have the boundary condition that x goes off to infinity. But if you have a finite, this is the better form. Really, it sure is. Okay, let's go ahead and solve it. If that's the form of the solution that we want to work with, And this I'm just going to say is theta naught for simplicity. Theta at x equal to 0 is theta naught, or theta base, I should say. Theta b. Okay. Use this boundary condition to determine C1. So we apply this boundary condition. I'm going to make it in color. So theta b, that's the theta at x equal to 0, is equal to C1 times the sinh of m times 0. What's m times 0? 0. What's the sinh of 0? 0. C1 can be anything. This equation will work. Plus C2 times the cosh of m times 0. M times 0 is 0. The cosh of 0 is 1. Guess what C2 must be for... did I do the wrong boundary condition? No wonder you're staring at me. I think I was supposed to do this boundary condition, because I can't conclude that that's equal to 0. It's just that I conclude that theta b is equal to C2. C2 is equal to theta b, not 0. My mistake. Should we grade everybody right? So it's not 0, it's theta C2 is theta b. All right. How about the next boundary, the next one? How do you apply this boundary condition? Well, you have to take the derivative. So we'll have the derivative of the analytic solution is equal to C1m. Instead of sinh, we get cosh of mx. And then I'm going to write it down here. Plus C2 is theta b. So we'll use that. M times the sinh of mx. We apply this at where? L. So this becomes L. This becomes L. And what does that have to equal? 0. So what is C1? The m's cancel. Isn't it going to be negative theta b? And then you're going to have the sinh of ml divided by the cosh of ml. Is that right? And so guess what sinh over cosh is? Hyperbolic tangent of ml minus theta b equal to C1. So now you have the full analytic solution. For what boundary condition? Insulated tip. So if I can, so we get that theta is equal to minus theta b hyperbolic tangent ml times the sinh of ml plus theta b cosh of, that's not ml, mx, of mx. Did I put it together okay or not? All right. Once I have that, it's not the end of the game. What I really want to know is what is the Q out the fin? How many watts of heat transfer is the fin accomplishing? Okay, there's two ways to calculate this. You can do it by convection off of the sides, or you could do it by conduction at the base, the BASE. Both of them will give you the same answer, but this one is a little harder. This one's a little easier. Well, let's pick the easy route. So if I have my fin right here is the base, and I want to know what is Q going into the fin. We know it's eventually convected off, but what is the going into the fin? Wouldn't that be given by Fourier's law at the base? So wouldn't the Q in the fin equal to minus K A sub C d theta dx evaluated at x equal to 0? Why did we not put temperature? Because we already showed that d theta dx is equal to dt dx. Okay. So now I have my analytic solution right here. What is the, we put minus k a sub c. What is d theta dx? Well, if I do, here, maybe I should write it out here. Let me get rid of this, right, make use of that space. What is d theta dx equal to? This is a constant, theta b. Hyperbolic tangent of ml is a constant. We have the sinh. Doesn't that give m times the cosh of mx plus theta b times m times the sinh of mx. Did I do that derivative right? Okay. So evaluate that derivative at x equal to 0. What is the cosh at x equal to 0? 1. What's the sinh at x equal to 0? 0. So that second term goes away. We're left with minus theta b, the hyperbolic tangent of ml times m. So what goes out the fin is simply, let me try and draw it this way. We're going to put the k a sub c times the m times theta b times the hyperbolic tangent of ml. The minus signs went away. Okay. What was m again? I forgot. M squared is hp divided by k a sub c. Thank you. That's it. So if I do this, if I put a an hp there and an hp there, then what is this one? That's 1 over m squared. M squared. Isn't that right? All right. And then I want to put an L here and an L there. One of these M's cancel. I'm going to have an ML in the denominator. And so what we're going to have is an H from this H right there. We have the perimeter times L. We're going to have theta b at the base, hyperbolic tangent of ml divided by ml. Bad looking ml. So we want to pause for a minute and just look at it. What is theta b? The temperature difference. Where's the fin the hottest? At the base. It can't, anywhere out as you go further out, it's going to only be cooler. But that would be the hottest temperature difference or the highest temperature difference. Okay. What is convection coefficient? We knew that one. What is P times L? Perimeter times length. Isn't that my convective area for the fin? And so a little name calling here is if the temperature anywhere in the fin was equal to the base temperature, then theta anywhere in the fin would be equal to the base temperature difference. And then the Q would be just H perimeter times L times theta B. That would be the maximum Q that the fin, if the fin was super high conductivity and everywhere was the same temperature. It was easily conducted down the fin. The heat is easily conducted. There's no temperature cooling as you go down the fin. This would give you that absolute maximum. And so right away they go, oh, look it. We have the Q fin is equal to some term times the maximum theoretically possible if the fin was isothermal and at the base temperature. Okay, guess what that eta looks like? It's the hyperbolic tangent of ml divided by ml. And they call this the fin efficiency. Now, this is the equation for the fin efficiency for one tip boundary condition, the insulated tip boundary condition. You can get the analytic expression for the other ones, but it's a little more complicated. So this is a big equation, as well as this is a big equation in fin heat transfer analysis. Okay. So a lot of fins are not round, they're rectangular. Let's just quickly review what a rectangular fin looks like. Like that. So you'd still have the X going out from the base from 0 to L. But for the conduction area, we would have a different equation. It's not pi d squared because of a pi d squared over 4 because it's round. But here we're going to have a thickness T and a width W. All right. In terms of T and W, what is A sub C? Isn't it just T times W? Yeah. All right. Harder one, perimeter. Perimeter. In terms of T and W, what is the perimeter? It's a 2T plus 2W. Exactly. And in a lot of cases, if T is much, much less than W, then the approximation is that P is equal to just 2W. That's exactly right. So sometimes you have a very thin rectangular fin compared to the width. And so there you go. Okay. Now, Professor, we love that simple equation when you have the insulated tip. But is it really a good approximation when I have convection off of the tip? Well, what you do is you have a corrected length, which is pretty easy to understand. Hopefully you see things like this and it makes sense to you. But if I took and cut right here and then flipped up and extended the length just a little bit and extended the bottom a little bit, right? I would cut it in the middle at the end and flip it up on two sides. How much would my extension be? For the insulated tip, if I still want to use those simple equations, I would use a corrected length. And it would be the actual physical length plus, would it be T over 2 or W over 2? Wouldn't it be T over 2? Yeah, it would be T over 2. Why isn't it T? Well, you cut it and you flip half of it up and half of it down. And so this is an equation for corrected length. And so a lot of times you'll see, oh, the fin efficiency is the hyperbolic tangent of mL sub c divided by mL sub c. And you're saying, where did that LC come from? Well, that's because they're putting it for a corrected length. What happens if I have actually it is truly insulated? Well, then you don't need the corrected length. It's only if it's convected that you just have this little addition for the length. All right. This is a radiator. If you look at it closely, where are the fins? This is a fin going back and forth, back and forth, back and forth, right? So what's happening in this passageway? Fluid's flowing, and it's creating a base temperature right in here. And so when you would do this, what you do is you would cut it down the side. You would ignore basically you'd have a bunch of little fins sticking out like that. And for these tips right here, so this is the base, and each of these are the tips of those fins. It's where it's cut. Do I need to use a corrected length for that? No, because it truly is symmetrical. Hence, it's effectively an insulated tip boundary condition. Because, you know, this side on there looks just like that side. This is an important table in the textbook, table 3.1. And what do? They have case A, B, C, D. All of them are for your tip condition. So if you have a convective heat transfer, isn't this the appropriate boundary condition for the tip? Well, then you're going to get a different temperature solution, analytic solution for the temperature. And here they put theta divided by theta B. That's fine. But it's a little more complicated than the adiabatic. Case B is adiabatic. That's the one we just solved for, isn't it? Here, theta over theta B is cosh, blah, blah, blah. Actually, they simplified it even more. They worked a little more on our analytic solution and simplified it than what I did. But what we did was sufficient. Okay, and then if you have the prescribed temperature, it's rare, but that would be another boundary condition. Here's the analytic solution. And here's the, I would say that this is the most popular, case B. This is the second most popular. And the others, you just want to avoid. I mean, that's the bottom line. I mean, you can code them up if you had a computer program and you wanted to do it that way, but everybody I've seen, they'll just take and forget the convective. They'll use the adiabatic tip with the corrected length. And that is a good enough approximation. Okay, but this is another popular one, so if you have infinitely long, and then you just get a very simple analytic distribution for the temperature. Now, over here, what do they have? The most important property is what is being transferred into the fin and then convectively off of the fin. So it's the fin heat transfer rate. And you see that this is a nice packaged simple solution. I don't really like the way they packaged it here. I think the way we did it is a little better because I like to put the fin efficiency. What was that? The hyperbolic tangent of ml divided by ml. If you like the corrected length, put a C on it and a C on it. Great. And then you use to calculate the Q, all you have to do is calculate Q max. That's easy to remember, times the fin efficiency. And then what was the Q max? Well, assume everything, the whole fin is at TB, the base temperature. So it would be Q max is equal to H times perimeter times L. You like to C on it? Fine. Put L sub C for corrected length. Gets the right area. Times theta B. Pretty easy to remember. And I find this a little less intuitive because you got to come down here and there's m, big M, and here's little m squared. There's a definition of little m squared. Okay, but there you go. So this is a nice table. Summarizes a lot on the heat transfer. Okay. Okay, there's another. We covered the fin efficiency, did we not? What was the symbol for that? Eta. You also have fin effectiveness. Epsilon, I believe, is the term used in the textbook. And just read the definition. Ratio of the fin heat transfer rate to the heat transfer rate that would exist without the fin, a bare base. And so this number hopefully is greater than 1. Because if you attach a fin and it's less than 1, that fin acted like an insulator. Which you could do, you don't want to do it, but it's hopefully like 2 or 5. That means it really promoted the heat transfer. by covering up some of the base, but you actually increased it. This is the more popular one, the fin efficiency. All right. Well, not all fins are easy to geometrically to analyze. Sometimes that area, the cross section, changes as a function of x. Here, for the pin and the rectangle, they were constant. But here, can you see that that area, when you're coming out, is changing for a round, fin like that? So they have solved these things, and they put the fin efficiency as a function of parameter grouping. And so you'd have to typically figure out what is L sub C, 3/2 of that times what is that, HK divided by K, AP to the 1/2. And here are the definitions. L sub C times T is AP, blah, blah, blah. Okay. So if you have something where it's not a uniform cross-section throughout the length, then often it's graphical. Or sometimes they have an equation. Here it is. Some of them are given by equations. So this is tapering off. Is it triangular? Here's our simple rectangular. Notice, if you zoom in on this, what did they put for the L on that? L sub C. So sometimes a student will get confused, like, why does this equation have L and this equation have L sub C? Well, I think the book just dropped in L sub C here. And look at, they give you the equation, isn't it L plus the half thickness? Yeah. All right. All right. This would be, yeah, because the perimeter is going to be 2t plus 2w. If w is large compared to t, then this gets knocked out. I'm not exactly certain why they put it here. But look at, here's the area, isn't it? 2w L's of C, that's when t is much less than w. You neglect that little ends for convection. This end and that end over there are neglected, just the top and the bottom. Okay. All right, you want to solve some problems? Aluminum, it's given a thermal conductivity for the aluminum. It's a rectangular fin. There's the physical length of 10 millimeter. Its thickness is 1 millimeter, and the width is much, much greater than the thickness given. So the base temperature is 100 degrees C, and the fin is exposed to a fluid T infinity of 25 degrees C. There's a convection coefficient. Notice we don't assume the convection coefficient changes over the area of the fin. It's a constant. H is constant over the entire area of the fin. Use a corrected length approximation with the adiabatic tip solution to determine what is that fin heat transfer rate per unit width. Now, anytime, again, per unit width, what I would do is I would just say pick W to be 1 meter or something like that, then work with it. And then your final answer would be, I picked 1 meter for the width. Okay, so if 1 meter is the width, what is the perimeter? 1 meter on the top, 1 meter on the bottom. 2W, that's 2 meters, right? Okay. Let's go ahead and get our parameter m, or m squared. Let's just do m, which is the square root of h p divided by k a sub c. All right, what is a sub c? Your width times the thickness. So 1 meter times the thickness of 0.001 meter. So it's 0.001 meter squared. All right, and then we have our K. So we can crunch this number, H, 100. Watts per meter squared Kelvin. Perimeter, that's 2 meters. Okay, I forgot to point out something. All right, what does this m stand for right there in this equation? a fin parameter known as M. You can almost pick up any heat transfer book, and when they do the fin analysis, they use M as a parameter. That's nice. That one book doesn't use M, and then the other book uses beta, and another book uses some other symbol for this fin parameter, right? But what does this M right here stand for? Meter. Right away, you got real confusion in equation. You're looking at, is this a parameter known as the fin parameter M, or is this a meter? Sometimes life is challenging. I think they introduced M as a fin parameter when they were doing everything in foot and inches. And there wasn't the confusion. Now we moved to SI, we still use M for our fin parameter, but we have meter for our length. So, okay, let's continue on. K is 180 watts per meter Kelvin. And then the area, 0.001 meters squared. Do the units work out? Kelvin, Kelvin, watt, watt, meters squared. Okay, so look at, if I do 2 meters, I have a meter here, a meter there, and that meter squared. So, what is my answer, and what are my SI units for this fin parameter M? It's 1 over M are the units. See that? Okay. Somebody want to run this number for me and see what you get? So we get 33.3 inverse meter. And so you look at that equation. M is equal to 33.3 1 over M. It's very confusing to some. Hopefully we've got that figured out. What is my corrected length? It's my actual length of 10 millimeter plus my half thickness, so 0.5 millimeter. That's 10.5 millimeter. That's equal to 0.0105 meter. Did I do that okay? Why did I go slow there? Because you can make a mistake on half a millimeter and 10 millimeters, etc. Okay, so what is the product of M L sub C? About 0.35. Okay, then we have to get the fin efficiency, which is the hyperbolic tangent of ML sub C divided by ML sub C. What does that come in at? It comes in at about 96.1%. Notice a lot of times these fin efficiencies are pretty high. There's every now and then you get a fin efficiency that's low, but most time it's pretty high. This is pretty high. It can't be greater than 1, can it? No, never will be. Okay, so now we go to our equation and we say, what is Q? It's equal to Q max times the fin efficiency. What is Q max? It's the maximum as if the entire fin was at the base temperature. Okay, so it's going to be my H times the perimeter times L sub C, isn't that my convective area, times the temperature at the base minus the fluid temperature. All right, I'm running out of space here. What is my H? 100. Perimeter, 2 meters. I'm dropping the units. L sub C, we already figured that out, 0.0105 meter. And then the temperature at the base, 100 minus the fluid temperature, 25. 151 watts, and then you said, hey, but we picked 1 meter width, so it's 151 watts per meter of width of the rectangular fin. 157, and then you multiply by 96.1%. Thank you. Okay, so then it comes in at 151. Oh, what about this efficiency? Well, you had to solve for it to get part A. That's the most direct route. And then what is that tip temperature? Now, that's a little more challenging. How do you find the tip temperature? First of all, it's not much cooler than the base temperature, is it? The base temperature is 100. It's just 95.6 degrees C. But how do you find that? You have to go back to our temperature distribution. Well, you're going to go back to this equation like this, right there. And then you would put in the L, or even L sub C. It doesn't really matter much. It's going to change it very little. Here and there, well, there it's already L, sorry, for X. And you can calculate then that temperature. And it comes in 95.6. All right. I need to solve another problem. So we have a compact heat exchanger. It has air passages that are 2 millimeter by 8 millimeters. So can you see that this is the air passage right there? And the air is flowing that way through our air passages. All right. The plates have a depth of 10 centimeters in the direction of the airflow. The passages are created by walls that are 1 millimeter thick and act as fins. So this is the thickness, and this part right here, as well as this part, they act as fins. Where the temperature over here is my base temperature, and it's symmetrical. So it's like this is a fin on the left, and this is a fin on the right. Okay. The wall conductivity is 200, so they're giving us the K for the material. The electronic components dissipate heat uniformly, both side plates, so that they have a uniform base temperature. So over here, this is TB of 45, and over here the TB of 45 degrees C. Air flows in the passages with a temperature T infinity of 30 degrees C. Even though the air is cooler on the inlet and warmer on the outlet, the average air temperature is just a simplistic T infinity of 30 degrees C. All right. The convection coefficient is 125 watts per meter squared C. Calculate the rate of heat transfer to the air in a single passage. Just one passage. So this is one passage right there. Okay. This really is a fin problem. It's disguised or hard to determine, but this is your fin. So let me do this. I'm going to back out and just focus on one side right there. So what do we have? It goes like this. And you don't even have just one fin, you have an array of fins, don't you? Okay. Now, the temperature at the base right here is 45, and the temperature of the base at the fin is 45. This exposed part is convecting just as well as everything along this side is convecting. So let me do this. If I'm looking at just half of it right here, okay, and I wanted an approximation, let's say the tip right here, I was going to say, you know what, that tip is around 45 degrees C. That means everywhere along it's all 45, 45, 45. What would be the answer to calculate the rate of heat transfer? You're neglecting the fin part of it. You're just saying it's isothermal. It's like the maximum. You're calculating the maximum. So Q max would be the total, if I do it for half an area and then multiply by 2, let's do that one so I don't have to, so I'll stay with it. So 2 times, what is this? It's going to be my thickness right here. What is this thickness, this distance right there? what is it again? 2 millimeters? Is it 2 millimeter? Yeah. It's, so 0.002 meters times this 2 millimeter times the width going back 10 centimeters, 0.10 meter. Won't that give me the area for just that part? And then what about the top and the bottom for the passage? It'll be for the top and the bottom, so I'll just do one of them. It'll be 4 millimeter times that 10 centimeter, close. You see that? It's bookkeeping, but I'm trying to get that area that the air sees as it flows through half of a passage. Then I multiply by 2, so I get the total area. Okay, I need to multiply this by the convection coefficient H, which was 125. And then the temperature difference, 45 minus 30. Did I do that okay? All right, if you have a calculator, can you run that number? All right, so let me pick it up here. Sorry about that equal sign, I got rid of that. So when you crunch this number, doesn't this come in at about 3 point, hold it, I need to stop and then show the results. 3.75? Yeah. So that's how many watts are transferred, 3.75 watts. That's assuming that it's the same temperature of 45 degrees everywhere that the air sees, okay? Okay, now, if you calculate it, where in counting for the thin nature of these protrusions sitting out here, then you're going to get 3.73. Now, we're going to do a lot of work fighting over that third significant digit, right? So whenever you're doing a problem like this, I encourage you to slow down, back up, assume it's like everywhere the same temperature, get a number, and then when you get into the forest, don't get lost because there's going to be a lot of calculations. Okay, so the first calculation, what I'd want to do is I'd want to get a fin efficiency for that one fin. All it is sticking out like this. What is this L right here? The length of the fin. Isn't that going to be 4 millimeters? And I don't need to use L sub C because it truly is insulated thermally. Okay, so I need to calculate my fin parameter M. That's going to be my H times perimeter divided by K A sub C. All right. I'm sorry, what? Square root. Yeah, square root. Thank you. Okay, so the H, we'll put in the 125. What is my perimeter? 2W plus 2T. What about that 2T? Well, let's neglect it. Isn't that right? Okay. What about the K? 200. What about the cross-sectional area for the conduction? That's going to be my W, 0.10. And then what about, isn't that going to be my T? I can't neglect that. And what was that, 2 millimeter? 0.002. Okay, that brings, oh yeah, 0.001. You're absolutely right, 0.001. That'll give me my parameter M. I multiplied by L. That gives me ML. Then this is going to be the hyperbolic tangent of ML divided by ML. And should I wait for you to calculate it to 3 significant digits? And we show the results. 0.993, 0.9934, and 0.994 will give credit. And 99.3, you didn't get it changed in time. 0.931, really? No, that's not right. 99, no. Something's off on those. So 0.993. You know, it's really close to 1. That's why an answer right here of 0.375 is so close to the right answer of 0.373, because it's only going to drop it a little bit. So now if I want to calculate the actual, what I do is I come and maybe I go slow again, is I'll say Q is going to be made up of two parts. One from the exposed base and one from the fin. All right? And if you think about it, it's like, well, are you going to do half of a fin and then this is the other half of the fin? Yeah, that's true. And then you have this whole base right there exposed. But let's go for it. So we have for the, if you want to, we'll do it like this, multiply by 2 for the sides. For the exposed base, wasn't that just 0.002 times 0.10? I mean, we're just repeating up here. Times, I'm going to now stop that. I'm going to come way over here. I'm going to put in my convection coefficient, 125, and my temperature difference, 45 minus 30. Okay. All right. Then we had 2 times 0.004 times 0.10. The only thing we're adding is an efficiency for the fin part, not for the base part. This is our base. This is for our fin, isn't it? And so you just take and multiply now by your 0.993. The base is still 100%, and then this is the finned part, right? So if you run that number, do you get 0.7 or 373? I'm sure you do. If I have an array of fins, let's stick them out like this, another one, and another one like that. Okay, and so if I have the heat transfer Q, it'll be off of the base, that unfinned exposed base, and then the Q off of the fins. All right. Well, just like we did, you have to get the convection coefficient, which is the same for both of those, but you have to get the area of the base and multiply by that temperature difference of the base. Where over here for the fins, you have the convection coefficient times the area of the fin times the theta of the base with one modifier, that's efficiency. You want this total Q to be represented by an overall efficiency times the area total. What do you mean by area total? Well, area total is going to be the area of the base plus the area of the fin. But just leave it area total for right now. Okay. Times the convection coefficient. Maybe I should have put an H there. And then theta base. H, A base, theta plus efficiency of the fin, H area fin, theta base. Okay, start canceling some stuff. Theta base goes on all of those, right? What about the convection coefficient? Cancels. What I can get now is an equation for the overall efficiency. Hey, what is that subscript on this eta right here? It's a subscript O. What's it for? Overall. overall efficiency. Overall, because it's a combined efficiency for the base and the finned part of it. Okay, so that's going to be the area base plus the fin efficiency area fin divided by area total Now, this doesn't look all that nice, but if I take and I add an area fin here, and I subtract area fin there, I will get something that the book has, because what is this? Whoops. That's going to be now 1 plus efficiency of the fin times, well, actually, no, I need this. Area fin times the efficiency of the fin minus 1 divided by area total. Or you put 1 minus the 1 minus the efficiency of the fin times the area of the fin divided by area total. I think this is the equation the book has. If your fin efficiency is 100%, 1.0, then what is the overall efficiency? 1. Okay, and if the area of the fin divided by area total goes to 0, basically you don't fin it, then the overall efficiency is 1 again. So this equation, I don't know, you could live without it. We solved the problem previously without it. Or you could use it. Either way. Yes, sir. They have capital N would be the number of fins times the area of one fin. Gives me the total area of the fins. How do you like that?
They have NAF.
NAF. And so that's one fin's area. Number of fins, right? All right. Well, it looks like I don't have enough time to solve another problem. Thank you for your attention. We'll see you next time.